Is that a satisfactory answer? Are there other questions? If not, I would like to continue the discussion of symmetries and conservation laws that we began last lecture by considering a new class of continuous transformations that are invariances of certain Lagrangians, extracting the associated conserved currents and the associated global conservation laws. This new class of symmetries I will talk about are not going to be universal. We believe on good experimental grounds that if we attempt to explain the world with a field theory, that field theory had better be translationally invariant and Lorentz invariance, and that led to the conservation of p mu and j mu nu. However, some field theories which people have invented to understand the world turn out to have larger groups of symmetries than just those associated with the Poincare group. They have groups of symmetries which in fact commute with space-time translations and with Lorentz transformations, and are given the somewhat deceptive name of internal symmetries. Internal meaning somehow you're doing something to the interior structure of a particle. You aren't moving it about in space or rotating it. The word is deceptive because, as you will see, it applies to theories of structureless particles, in particular to free field theories. Nevertheless, the nomenclature is standard, and I will use it. As a simple example of a theory that possesses an internal symmetry, let me take a free field theory involving a set of scalar fields. All of them free and all of them with the same mass. And to the simplest non-trivial case, I will let the index range over only variables 1 and 2. So this is simply a sum of two free Lagrangians, each of them for a free scalar field of mass mu, and there are two such fields, and I have left out the 1/2. Now, this theory possesses a rather obvious symmetry. Since everything involves the quadratic form phi1 squared plus phi2 squared, this is invariant under a group that is isomorphic to the two-dimensional rotation group of Euclidean geometry, SO2. Not two-dimensional rotations in the xy plane or in the yz plane, but in the 1-2 plane, between the fields phi1 and the fields phi2. To be particular, for any lambda, if I make the transformation phi1, I'll keep x fixed, it doesn't participate in the transformation, goes into phi1 cosine lambda. Now let me see how I defined the sign at the beginning. Yes, plus phi2. Of course it doesn't matter, but I want to stick with my conventions on the blackboard, so on my notes, so I can catch myself if I make numerical errors. Phi2 goes into cosine lambda minus phi1 sine lambda. The Lagrangian is obviously unchanged by this. There it is. It is a symmetry of this particular sample Lagrangian. And it's not connected in any way with geometry. It's not a spatial translation, and it's not a Lorentz transformation. Of course, I could write more complicated Lagrangians, which still possess the same symmetry. For example, I could add to this plus some, well, maybe I should say minus, so it'll come out with a positive sign in the energy. Phi1 squared plus phi2 squared, quantity squared, or cubed, or to the 5th power. And that would still be invariant under this transformation because phi a is invariant under this transformation. The sum of the squares is preserved by rotations. Is there any question that this Lagrangian has this symmetry? Okay. Now let us extract the consequences of it. I've written it down. It's just a sample. but let's see how we, let's feed it into our general machinery, turn the crank, and see what happens. Well, in terms of the general formulas introduced in the last lecture, d phi 1 equals, I hope nobody confuses the upper index 2 with a symbol for squared. Please don't make that mistake. d phi 1 equals phi 2, and d phi 2 equals minus phi 1. We also need the canonical momenta, or I should say those four vectors, of which the canonical momenta is the fourth component. Pi mu 1 equals d mu phi 1, and pi mu 2 equals d mu phi 2. We also need the four-component object I called f mu last time, and of course, since the Lagrangian is unchanged, f mu is trivial. F mu equals 0. The change in the Lagrangian is a divergence of a four-vector, and that four-vector is 0. Thus, we can construct the current by our general formulas. J mu equals pi mu a d phi a minus f mu equals d mu phi 1 times phi 2 minus d mu phi 2 times phi 1. This is, of course, the formal classical expression. We will later investigate whether or not it has to be normal ordered. In the case where we can investigate, where g equals 0. In the case when g equals not equal to 0, what we have to do to make sense of this is a subject we will investigate much later in the course. Now, in the case when g equal, the associated conserved quantity, Q, is, of course, the integral of d cubed x of the 0 component of this, i.e. d0 phi 1 phi 2 minus d0 phi 2 phi 1. Let's compute this in the case where we can compute things, that is to say for a free field theory, where g equals 0, and I remind you to your infinite boredom, phi of x and t equals integral d cubed k square root of 2 omega k. I should really write this formula on a piece, have the draftsman write this formula on a piece of cardboard, which I could nail up there. ak e to the plus I k dot x minus I omega k t, and out of boredom, plus Hermitian conjugate, just to keep from writing the A adjoint term again. You've all seen it so many times. Well, by our usual tricks, we can compute Q. It's exactly the same calculations as a million others we've seemed to have done. We only have a single integral d cubed k. The 2 pi to the 3 halves get eaten up in the delta function. We have 2 omega k. And then what do we have? Oh, I should say there are 2 phi's, of course, 1 and 2. And therefore, there are 2 sets of annihilation and creation operators, which I'll indicate by 1 and 2. Well, we can have two kinds of terms. We can have an annihilation. Once again, there's no need to keep track of 2 annihilations and 2 creations. Those must cancel by a time independence. So we can have AK, well, let me write it this way. AK2, AK1 adjoint times some coefficient, which I'll shortly compute, plus AK2 1 adjoint AK2, again times some coefficient, which I will shortly compute. Notice there's no need to worry about which order they come in, because since you've always got a product of a 1 field and a 2 field, you always have the product of a 1 operator and a 2 operator, and those always commute. So I've written it already in, whoops, I haven't. What have I done? I wrote the same thing twice, forgive me. Okay. So I've written it already in normal ordered form, not that it matters. Well, what are the coefficients here? Firstly, we can pick up a AK2 adjoint from the phi 2 term here, in which case we must pick up the A1 operator from here, and that gives us a minus I omega k from the differentiation. Okay, then we can pick up the A2 adjoint from here, in which case we get a plus I omega k from the differentiation, but we have a minus sign in front. That takes care of all of these terms. Likewise here, if we pick up the AK1 adjoint from a differentiated operator, we get an I omega k. If we pick up the AK2, and that happens in the first case, if we pick up the AK2 from a differentiated operator, then we get a minus I omega k, but there's a minus sign in front. Thus we get a very simple expression indeed. There's an overall minus I, integral d cubed k, the 2 omega k's cancel, AK 2 adjoint AK1 minus AK1 adjoint. AK2. This is a very nice expression. It satisfies all the properties you would expect: an internal symmetry, a transformation that commutes with Q to satisfy. It is obviously Lorentz invariant. It commutes with the energy and commutes with the momentum. Unfortunately, well, perhaps I should stop here and ask if there's any questions about the computation. Yes, sir.
You explained this last lecture, but I missed it. Why are there the other terms, so the two creation operators and the two?
Oh, well, we know on a priori grounds that they must vanish because their coefficients would involve oscillating factors that have no hope of canceling.
Yeah.
And this thing is supposed to be time independent. So in particular in Fourier space, that means it has no such oscillating factors. So we just save ourselves a little labor by not continually checking that those ones cancel. If you wish, you can compute them and see them canceling.
How is that we've gone from an integral over x to an integral now?
Because we have two fields. One of them involves an integral d cubed k of a bunch of junk times e to the I k dot x. The other involves an integral d cubed k prime, let us say, times another bunch of junk, times an... And the whole thing is to be integrated d cubed x. The x integral is trivial and turns this into a delta function of k minus k prime, which kills one of the k integrations. Okay, this was the procedure I went through in detail for the derivation of the form of the energy in terms of annihilation and creation operators. Are there other questions? Now, this expression is nice, but it is hardly transparent. This is some operator that, for example, it annihilates the vacuum. It acts on a turns one particle states into one particle states. It turns a type 2 state into a type 1 state. This annihilates the original type 2 particle. This replaces it with a type 1 particle with a certain coefficient, vice versa with 2 replacing 1, etc. but it still is not a pleasant thing to look at, and one can make it appear much simpler by defining new annihilation and creation operators, which are linear combinations of the A's, of our original A's and A1s and A2s. We'll define BK as AK1 plus I AK2 over root 2. BK adjoint is, of course, the adjoint expression. The root 2 is there for a reason that will become clear shortly. Likewise, I will define CK as the other obvious other combination. These are also annihilation and creation operators. They create particles. If we look at the right-hand pair of equations, for example, these simply create particles in states that are a linear combination of a one-state and a two-state. And it is easy to check that they obey also the commutators for independent annihilation and creation operators. All the commutators vanish except for BK prime adjoint, which is equal to CK prime adjoint, which is equal to delta cubed of K minus K prime. I inserted the square root of 2 in the denominator so that it would come out delta cubed rather than 2 delta cubed. All others 0. If it's not obvious to you that all others are 0, let me do a typical combination. Well, obviously, any annihilation with any annihilation is 0. Any creation with any creation is 0. So let's take this annihilation with this creation. We get a certain term with a +1 coefficient from this with this, and the same term with a -1 coefficient from this with this. And we get 0. Likewise for the other cross term. The reason why these obey the same algebra is that they are annihilation and creation operators for orthogonal single particle states. For any given value of k, there are two states, which we called arbitrarily the one-type particle and the two-type particle, the type 1 meson and the type 2 meson. Of course, whenever we have a degenerate subspace of states, we are perfectly free to choose a different orthogonal linear combination to be our basis vectors. And here we have chosen the combination created by this, a linear combination of a one-type meson and a two-type meson to be a B-type meson, and the combination created by this, the orthogonal linear combination, to be a C-type meson. It doesn't matter if we have a Fock space with two degenerate kinds of particles, which two independent vectors we choose to be our fundamental mesons. Yes, sir, you have a question.
You mean that adjoints?
Oh, yes, I'm sorry. Someone should have called me on that. Of course I mean to have adjoints. Is this point clear to everyone? I could just as well have chosen, sine theta and cosine theta here, cosine theta and minus sine theta there. The algebra would have worked out the same. Why do I choose this combination? Well, I choose this combination because in terms of these operators, let's see. I'm reaching that terrible stage where, well, it's this, but keep this expression. The Q equals integral d cubed k. I'll write it down, and then we will be able to check it by eyeball. BK adjoint BK minus CK adjoint CK. That is, these mesons are eigenstates of Q, the B and C type mesons. Once I've written it down, it's easy to check it. We just do the combinations, the 1, and cross term up here, cancels the 1, 1 term up here. Likewise, the 2, 2. And the 1, 2 cross terms give me exactly the formulas I have on the board for Q. Thus, we have a much simpler interpretation of Q. We have a theory with two kinds of particles. We have, so to speak, diagonalized Q by writing this expression, or made it easy to see what the basis vectors that do diagonalize Q are. We have two kinds of particles. One of them, regardless whatever of its momentum, carries a value of Q plus 1. The other carries a value of Q minus 1. All of the Q is simply the number of B-type particles in a given state minus the number of C-type particles in a given state. And the value of Q does not depend on the momentum of the particle. We have no k-dependent coefficient here, just some overall k. This is very similar to the structure of electric charge. These particles, for example, could be pi plus and pi minus mesons, and this could be electric charge. We have two kinds of particles, one of which carries positive electric charge and the other of which carries negative electric charge, and the total charge of the system is obtained by counting the number of particles of one kind and subtracting the number of particles of the other kind. For this reason, I call this charge. Just to remind you of that, but that's just something to remind you. We haven't done anything like deduce the conservation of electric charge or anything like that. I have simply cooked up an arbitrary example which has asymmetry, which leads to a conservation law that has some structural resemblance to the conservation of electric charge. I said pi plus and pi minus mesons. I could have said electrons and positrons, aside from the fact that electrons and positrons have spin. That also has this kind of structure. But that I said electrons and positrons just to show you that it needn't be electric charge. If it were electrons and positrons, I could have said lepton number and called this thing lepton number instead of charge. That also has that kind of structure. Are there any questions? Now, introducing, I see I have an equation written down here that I meant to write down at an earlier stage. That's an obvious equation. H equals integral d cubed k omega k bk adjoint bk plus ck adjoint ck, easily obtained by substitution, and simply the obvious statement that the B-type particles and the C-type particles have the same mass. Now, I've introduced these complex combinations of the original A1s and A2s to simplify the representation in terms of annihilation and creation operators of this charge. However, it's suggestive, and therefore I would like to digress for around 15 minutes in a direction that really has nothing to do with symmetries, but has something to do with putting together two real fields to make a complex field, and talk for a while about complex fields. This is very suggestive. Suggests that maybe we should make this complex combination not just on the level of the annihilation and creation operators, but on the level of the fields themselves. That might make things look even simpler. Therefore, let me define psi to be equal to phi 1 plus phi 2 over root 2. And psi star, properly I should say psi adjoint, but the star is traditionally used for this purpose in the literature. Over root 2. Psi and psi star, of course, have representations in terms of creation and annihilation operators. Psi equals integral d cubed k over 2 pi to the 3 halves, 2 omega k to the 1 half, e to the minus I k dot x, times what? Well, 1 plus I2, and that gives us, of course, bk. Now, what about the creation operators? Well, there it's the same story. It's 1 plus I2, and therefore we get ck adjoint. Therefore, we have introduced a field, and of course, psi adjoint, psi star is the adjoint expression. We have introduced a field which, so to speak, has a nice, pretty commutator with Q. Our old fields, if you commuted phi 1 with Q, you'd get phi 2 with some coefficient. If you commute phi 2 with Q, you'd get phi 1 with some coefficient. Here, if you commute psi with Q, you just get Q with psi again with some coefficient. This psi is an operator that has definite charge-changing properties. It always lowers the charge by +1, either by annihilating a B particle or by creating a C particle. It has the option of doing either one, but whichever one it does, it lowers the charge by +1. Likewise, psi star is a pure charge-raising field. Like every free field, it can both annihilate and create, but it either annihilates a particle of charge -1 or creates a particle of charge +1. The psi and psi star also have very interesting equal time commutators and equations of motion. Of course, for the free field case, since they're linear combinations of phi 1 and phi 2, which obey the Klein-Gordon equation, psi and psi star also obey the Klein-Gordon equation. And their equal time commutators are easy to compute. Psi, of course, commutes with itself at equal times because it's a linear combination of phi 1 and phi 2, which commute with themselves and each other. So does psi star with psi star, but I won't bother to write that down because that's the adjoint equation. And so does psi with psi star, again, just because they're phi 1s and phi 2s. More interesting is psi of x and t with d naught, psi of y and t. That happens to be 0, because we get a certain term with a coefficient +1 from this, and the same term with a coefficient -1 from this. Likewise, the adjoint equation, which I won't bother to write down explicitly. Indeed, the only non-zero commutator is psi of x and t with d0 psi star of y and t equals, well, I get the appropriate term with coefficient +1 from here, +1 from here, the two root 2's combined to cancel the 2 in the numerator, and I get simply I delta cubed of x minus y. And likewise, although I won't bother to write it down explicitly, for psi star with psi. Now, why did I bother to do all this? Well, you'll see why I bother to do all this, where I make a big step and re-express the Lagrangian in terms of psi star. The Lagrangian, you recall, was 1/2 d mu phi 1 d mu phi 1 plus 1/2 d mu phi 2 d mu phi 2, which could just as well be written no 1/2 d mu psi star d mu psi, the missing 1/2 being supplied by the square roots of 2, minus mu squared, again without a 1/2, psi star psi. Now, if we look at this structure and read it backwards, it looks very much as if these are equations we could get by doing something that at first glance seems extremely silly. Starting out with this Lagrangian expressed in terms of psi and psi star, and doing the ultimate dumb operation of treating psi and psi star as if they were independent variables, not in fact each other's complex conjugate. By varying with respect to psi star, we would obtain, of course, the Klein-Gordon equation for psi. By varying with respect to psi and integrating by parts, we would obtain the Klein-Gordon equation for psi star. Treating psi and psi star as independent variables, we would find that the canonical momentum to psi was d naught psi star, expressed in this equation. The canonical momentum to psi star was d naught psi, expressed in the conjugate equation, which I have not bothered to write down. We would find, of course, that psi and psi star commute at equal times because they're Q-type variables, and that psi and d naught psi commute at equal times because they're the Q for one variable and the P for another variable. So if we had been done to treat psi and write this thing in terms of complex fields to begin with, and treat psi and psi star as if they were independent operators, we would have obtained, in this particular instance at least, exactly the same results as we obtained by doing things correctly, treating phi 1 and phi 2 as real independent variables. Are there any questions? That explains why I went through the sequence of computations which had you all baffled as to motivation. Yes?
Why is that a dumb approach?
Well, it turns out it is not a dumb approach. Well, because you can't vary psi and psi star independently, for example. Psi star is the conjugate of psi. However, I will show you that is in fact not dumb. I will begin, I will not complete. Once you see how the first part of it goes, the rest of it will be a trivial exercise for you to complete, to show that in fact you always get the right results if you have a Lagrangian expressed in terms of complex fields and simply treat psi and psi star as if they were independent. Yes?
Well, why is it not legitimate to treat them as independent?
Because psi star, yeah, I'll show you. I'll show you it is legitimate. If you already see it's legitimate, that's wonderful. Take a nap for the next 3 minutes. Okay? For those who may be more skeptical, I will sketch out the beginning of why it is legitimate. I will show that it is legitimate as far as the derivation of the Euler-Lagrange equations. Once you see my method, you will see that the same method can be used, carried through for the derivation of the Hamiltonian form, the equal time commutators, etc. So, I have a Lagrangian that depends on a set of fields, psi and psi star, complex conjugates of each other, the gradient of psi, and the gradient of psi star. For most practical purposes, this Lagrangian is so set up so that the action integral is real, guaranteeing that the Hamiltonian will be Hermitian when we're all done with quantization. That's not going to be necessary to the proof I'm going to to any of the proofs I'm going to give, but I might as well point it out. This is not, in practical cases, this is not a completely general function of these variables. Now, suppose I were to go through the variational procedure that leads to the Euler-Lagrange equations, treating psi and psi star as just varying psi and varying psi star. And I would get delta S is the integral d4x of some god-awful mess obtained by doing all my integration by parts. I'll just call it x to indicate I'm not concerned about its structure, times delta psi plus the conjugate god-awful mess times delta psi star. Nobody can fault me on that. Now, if I were foolishly to treat delta psi and delta psi star as independent, that is, if I were to consider variations, first delta psi arbitrary, delta psi star 0, obvious nonsense because psi star is the conjugate of psi. I can't vary them independently. I would obtain an equation of motion which tells me that x star equals 0, x equals 0. Likewise, by making delta psi star arbitrary, delta psi equals 0, that is to say, treating them as if they were really independent variables, I would obtain x star equals 0. And those would be my two Euler-Lagrange equations of motion. Now, this is obviously illegitimate. I cannot keep vary psi without simultaneously varying psi star because they're conjugates. However, what I can certainly do is choose matters. This is false. I can't do this first. This is true. I can certainly choose delta psi equals delta psi star. That is to choose my variation to be arbitrary but real. From this I deduce x plus x star equals 0. That's legitimate. I could also choose delta psi equals minus delta psi star, i.e. choose my variation to be arbitrary but pure imaginary, from which I deduce x minus x star equals 0. Now the consequences of this correct procedure is exactly the same, of course, as the consequences of the manifestly silly procedure. I leave it for an exercise for you to carry out all the other steps of the canonical program, the introduction of Hamiltonians, of momenta and Hamiltonians, and the working out of canonical commutation relations, and show that in general it all comes out the same as if one had treated del psi and psi star as independent variables. Yes, Kay?
Just one thing. In your formula for the variations as, why does the coefficient on the right turn out to be x star?
Well, it wasn't necessary in my proof, of course, as I say. That's because s equals s star. So since delta psi is the change in s has got to be a real quantity.
Okay.
Another way, a somewhat slicker way, let me say this, and then you can ask your question. A somewhat slicker way of saying the same thing, I went through this detailed argument, but a somewhat slicker way that you may find less plausible is to say that it doesn't matter as far as the formal derivations of the equations of motion and everything else goes that the Hamiltonian is Hermitian. I mean, of course, we get a nonsense theory if the Hamiltonian is not Hermitian. We don't get conservation of probability, but as far as all of those formal manipulations involving Hamilton's equations go, it doesn't matter that the Hamiltonian is Hermitian. So we could just as well consider psi and psi star as being independent variables all the way until the very last step, and then say, no, we're only going to look at the case where they're the conjugates of each other. And certainly as far as all of our formal equations go, so it doesn't matter. But you will probably, those of you of a skeptical bent of mind will probably not be convinced until you go through what I suggested earlier and go through the whole thing with real and imaginary parts and reassembling them. Now, there was a question that I postponed. Yeah?
I'm not exactly sure how something with that constraint of the variation is really to be sure you're minimizing the action.
I'm stationarizing the action. You mean stationarize, not minimize.
Right. Right.
Well, I can, if it vanishes, it must vanish for arbitrary variations. I consider in particular arbitrary real variations and arbitrary imaginary variations.
It seems to me it's like a constraint, though. If you could,
No, in the level of classical Lagrangian mechanics, I can put in any variation I want and deduce equations.
you have to include all variations.
That's right. Well, every variation is a linear combination of a real and an imaginary one. Now, just to show how this works, I'll rederive the form of the current starting from the psi star formalism. every lambda, let's remember how our transformations worked in our original basis. Phi 1 goes into phi 1 cosine lambda plus phi 2 sine lambda. Phi 2 goes into phi 1 sine lambda minus plus phi 2 cosine lambda. Thus, psi equals phi 1 plus I phi 2 over root 2 goes into, well, let's gather together terms. Phi 1 times e to the I lambda over root 2. That's cosine lambda plus I sine lambda, a trivial summation, plus I phi 2 e to the I lambda over root 2 equals psi e to the I lambda. Thus, we have a very simple expression for d psi. It is simply I psi. Likewise, by considering the transformation properties of psi star, or by taking the conjugate of this equation, d psi star is minus I psi star. These are two of the ingredients we need to construct the canonical current. The other is the respective conjugate momenta. I'm not labeling them by 1 or 2, so I'll say the 4-vector conjugate to psi is obtained by differentiating the Lagrangian with respect to psi, and is therefore d mu psi star. The 4-vector associated with psi star is d mu psi. That's the derivative of the Lagrangian with respect to d mu psi, considering psi and psi star as independent. F mu, of course, is still equal to 0 whether we express the Lagrangian in terms of phi 1 and phi 2 or in terms of psi and psi star. The current is therefore d mu phi star, psi star, I times psi, this momentum times the change in this field, minus I d mu psi times psi star. On the classical level, it is an elementary substitution using these formulas to show that this is the same current as before. The phi 1 terms all cancel between here and here. The cross terms come in with opposite sign in this thing and are and come together. Phi 1, phi 2 cross terms, and the square root of 2's in the definitions takes care of the fact that each cross term comes in twice. Work it out if you don't believe me. On the quantum level, for a free field, it is in this case necessary to normal order in order to get the same result as before, because when we write things in this way, the psi and psi star, of course, psi and d mu psi star do not commute, and therefore to make sure all of our annihilation and creation operators are in the right place, we have to normal order. This concludes the discussion of complex fields. Are there any questions? In the first term, no. Yeah, sure. L is T minus V. We want V to be positive, so the energy is unbounded below. No, it was originally minus. It was always minus. If I wrote a plus, it was a slip of the chalk. It's always minus. L is always T minus V, the terms with time I phi 2. Okay? Yes, the minus in the rotation. This is is just another way of saying that psi commuted with the q just gives you psi again. That psi is a charge lowering operator. Now, I discussed a very simple example involving internal symmetries in which there were only two fields. And I had a long digression on the method of complex fields, which enables us to simplify somewhat the representations of things in that simple case. We can, of course, consider much more complicated internal symmetry structures. Indeed, we get much more complicated internal symmetry structures simply by writing down formally back to real fields the same expression we had before, including my error, I am told, minus sign, minus mu squared over 2 phi a, and possibly some interaction, g phi a squared. And now let a run not over 1 to 2, but 1 to some number n, your choice. In the same way that the previous theory was invariant under SO2, this is invariant under SON, the group of all orthogonal transformations on n real variables. The connected group of all orthogonal transformations on n real variables. We can imagine these vectors, these fields, as being labeled by vectors in some n-dimensional space, internal space, imaginary space, fictive mathematical construction, and then for every rotation in that n-dimensional space, there is a transformation of the fields among themselves that leaves the Lagrangian invariant. We can go through the elaborate procedure of constructing the currents, but I hope you know enough about the n-dimensional rotation group to know that a complete and independent set of infinitesimal transformations are rotations in the 1-2 plane, rotations in the 2-3 plane, rotations in the 1-3 plane, etc., each of which is something we have done with a slight relabeling. So therefore, we will obtain n times n minus 1 over 2 conserved currents, because we have n choices for the first number that labels the plane, n minus 1 for the second, and of course it doesn't matter what we call first or second when we're labeling a plane. And the form of these currents, say the current corresponding to a rotation in the AB plane, will be exactly the same as before, d mu phi A times phi B minus d mu phi B phi A. That's the same, that's just 1 and 2 replaced by A and B, and as you see there are only n times n minus 1 over 2 of these currents that are independent, because when A equals B the current is 0, and if I interchange B and A I just get minus the same current. There is no analog here of the trick of complex fields in this more complicated case. And the reason is very simple. The trick of complex fields was based on diagonalizing the charge. Here I can hardly expect to diagonalize all the charges simultaneously, because the corresponding infinitesimal transformations do not commute. A 1-2 rotation does not commute with a 2-3 rotation. And therefore the corresponding charges should not commute. Still, for some cases, it is nice to pick one charge as one of this n times n minus 1 over 2 charges as a nice charge and write things to diagonalize it. And the others remain ugly and awkward. For an example, n equals 3, where we have 3 degenerate particles, it is frequently convenient to focus to diagonalize arbitrarily the 1-2 charge, that is to say, introduce fields psi equals phi 1 plus I phi 2 over square root of 2, psi star equals phi 1 minus I phi 2 over square root of 2, and a third one, usually called phi naught, which is simply equal to phi 3. And then in terms of 1-2 charge, this lowers 1-2 charge by 1 unit, this raises it by 1 unit, and this doesn't change it at all. This either creates negatively charged particles or annihilates positively charged particles, vice versa for this, and this creates and annihilates neutral particles, whence the subscript naught. This notation in practice most frequently occurs when we consider the system of the 3 pi mesons, which in the absence of electromagnetism and the weak interactions, as you probably know from other courses, would be degenerate in mass. And indeed, this is due to a group with precisely the structure of SO3 called the isospin group that you may or may not have heard of, that acts in exactly the prescribed way on the 3 pi mesons. Of course, the pi mesons interact with a lot of other particles, so there's plenty of plus dot 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 out here. The 3 pi mesons, and the reason we pluck out the 1-2 subgroup is that when we introduce electromagnetism, the full SO3 invariance goes away, but this 1-2 invariance remains and corresponds to the conservation of electric charge. This is how you embody those ideas, which I presume you have seen in other courses or read about in Scientific American articles, into a context of a field theory. Yes, sir?
Is it SON rather than ON just to fill the things with negative terms?
Yes, we'll talk about them later. Those are not associated with infinitesimal transformations since they do not lie on continuous paths going to the origin.
But I think that this is ON continuously.
SON just means the continued connected part of ON. S means specialized to determinant 1, or specialized to the connected part. Now, we will talk about the full ON group, or more probably just the full O2 group at a later stage, maybe the end of this lecture when we stop talking about continuous symmetries and start talking about discrete ones. Now, however, I will abandon continuous symmetries. Well, I won't abandon them. They will recur as a theme again and again in these lectures. But before I abandon the general discussion, there is one gap in our arguments. And that is, I have not discussed the Lorentz transformation properties of the charges built up out of these currents. You expect from the examples I have given you that the Lorentz transformation properties are the same as those of the currents, except one index is annihilated. That is to say, here where we have a current that transforms like a 4-vector in the case of charge, the associated conserved quantity is charge, which is a scalar. When we have a 2-component object, a 2-index object, the energy momentum tensor, the associated conserved quantity is a 1-index object, the total 4 momentum. When we have a 3-index object, that mu nu lambda that I talked about before, the angular momentum currents, the associated object j mu nu is a 2-index object, a tensor. But we haven't proved that. I mean, we've proved it in particular cases by writing explicit expressions for these objects and showing that they transform, whereupon it is manifest that they transform in the desired way, but we haven't shown it in general. So let me now attack the general problem of, if we know how a current transforms, how does the associated charge transform? I will do in detail the case only of an internal symmetry current. Once I do it, you will see, just by in your eye adding extra indices to the equations, how the whole thing works out for the energy momentum tensor and the angular momentum current. I have a conserved current, d mu j mu equals 0. I will assume it transforms, as in the case of an internal symmetry, like a vector field. That is to say, under a Lorentz transformation, lambda j mu of x goes into lambda mu nu j nu, of lambda inverse x. Remember when we were discussing field transformation laws, we said there's always an inverse operator in here, but the uninverted thing outside. Now, this will be my only input. This could be either in classical physics, in which we say we take some field configuration, and then we Lorentz transform it, and the current transforms in this way. Or this could be in quantum mechanics, where this transformation is affected by a unitary transformation. Since all the equations I manipulate will be linear in J mu, it will be irrelevant whether J mu is a C-number field or an operator field. Now, we define Q as integral d cubed x J0 of x and any time. So just for notational convenience, I will choose the time 0, since it is independent of time by the conservation equation. Since we know how lambda transforms, we know how Q transforms. It will go into some object, which we will compute in a moment, and which I will denote by Q prime. The question we wish to ask is Q prime equal to Q? That is to say, in this case, is the current a scalar? Now, in order to make this work, I will have to rewrite the expression for the current. In a way that makes its Lorentz transformation properties more evident, and therefore I will write Q equals integral d4x delta of x naught, turning it into a time integral, n dot j of x, where n is the unit vector pointing in the time direction. This is simply a fancy way of writing j naught. This is simply a fancy way of writing integral d cubed x at x naught equals 0. A perfectly equivalent way of writing the same thing is integral d4x d mu theta of x naught, theta of n dot x, j mu of x, because the space derivative of this theta function is 0, and the time derivative of, it gives us the delta function. X naught equals n dot x, of course. This form may make you feel a little nervous, because it looks like we can make this object equal 0 by integrating by parts. But of course, we do not have control over the time boundary conditions, and theta is 1 for all positive x, so we can't get rid of the time boundary in the time integration by parts. I will now write a corresponding expression for Q prime. Equals integral d4x. Oops, I've forgotten how the argument goes. Hold for a moment while I turn to my ever-reliable aide-memoire. Delta of n dot x. Notice we do not change the integration surface. That would be a no-no. To change both the current and the integration surface would obviously give us the same answer. That is not what we are doing. We are taking an active view of transformations. We change the field configuration and then do the same experiment on the transformed field configuration. So we are measuring the same Q prime, the same Q defined in exactly the same way for the transformed current. So this part stays unchanged. Likewise, the fact that we have n dot j here is there, but we have n dot lambda j. That's the lambda mu nu here, written out in compressed notation of lambda inverse x. That is the same integral of the same component, the time component, for the pattern of currents corresponding to the transformed field configuration. Now, in this form, it is easy to see what Lorentz transformation, how to make this look more comparable to Q. We define x equals lambda x prime, that being the definition of x prime. We define n equals lambda n prime, that being the definition of n prime. We plug this in, and we find, and of course, from this it follows that n dot x equals n prime dot x prime. We plug this into our integral, and we find q prime equals integral d4 x prime delta of n prime dot x prime n prime dot j of x prime. Since n dot lambda j is lambda n prime dot lambda j, which is n prime dot j by the Lorentz invariance of the inner product.
Did you write the inverse from x, you definite x is lambda inverse x prime?
Oh, yes, I did. X is lambda x prime is lambda inverse x.
And then does the following equation hold?
Yeah. Lambda x prime dot lambda n prime is x prime dot n prime. That's the Lorentz invariance of the inner product. Now we can write this in terms of a d mu, because by the same reasoning as gets us from this equation to this equation, this is, dropping the primes on the x's, my privilege, since it is just an integration variable, and I can call it what I please. This is integral d4x d mu theta of n prime dot x j mu of x. Thus, the object we wish to compute, which is q minus q prime equals integral d4x d mu theta of n dot x minus theta of n prime dot x times j mu. Now integration by parts is legitimate, because this quantity in brackets, although not 0, certainly goes to 0 at any fixed x as time goes to infinity, because eventually n dot x becomes positive, and n prime dot x also becomes positive. This is equal to 1, and this is equal to 1, and difference vanishes. Likewise, x goes to plus infinity, and x naught goes to minus infinity. Eventually, this one becomes negative, and this one also becomes negative, and again, the differences cancel. 0 minus 0, and it vanishes. So in this case, we can I see puzzled faces. Perhaps I had better make a drawing. Here's space-time. Here's the surface n dot x equals 0. Here's the surface n prime dot x equals 0. Some Lorentz transformed plane, which I've drawn badly since I see I have drawn it as time-like over the 45-degree line. So let me sketch it more like this. Okay? The difference of the two theta functions is plus 1 in here, where you're above both the n dot x prime but below the n prime dot x prime, minus 1 here, where you're above and below in the opposite order. 0 here when you're above both, so both of these are equal to +1, and 0 down here when you're below the other, so both are equal to 0. Okay? Therefore, I can integrate by parts in time without worrying about boundary terms. And this equals integral d4x, square brackets as above, d mu j mu equals 0, QED. Thus, Q prime equals Q. I've constructed this argument in this way, so you can readily see that hardly anything is changed if I had a tensor current, conserved current in here. If I had a tensor current, all that would happen would be that I would have an extra index with an extra Lorentz matrix on it, which I would never ever play with, which would just go through all of these equations, hanging on, playing no role in any of my manipulations, except to emerge at the end to tell me that P mu was a 4-vector. Yes, sir?
I see the same thing just from the second line where you find so integral d4x d mu at theta. Theta of n dot x is or is not a Lorentz invariant to the extent that n dot x is a Lorentz invariant. And then you contract d mu with j mu and you get a scalar. So the whole thing is a scalar right away. Is that correct or is that...
No, that is incorrect because I am not transforming n. The Lorentz transformation changes the current, but I am integrating over the same...
I am arguing that your integral is a Lorentz invariant quantity just from the fact that you are contracting...
This is just another way of writing delta of x naught.
I appreciate that, but if you contract the two indices because they are on the same...
No, when I make a Lorentz transformation, I change the fields, but I don't change the observer. So n stays fixed. N does not Lorentz transform. The procedure you are suggesting would correspond to both transforming the fields and transforming the observer. Okay, that is just a change of coordinates. That, of course, always gives the same result whether the theory is Lorentz invariant or not. Okay? That's just like passing. If you transform the coordinates of the observation and of the observed system, and you transform the coordinates of the observer, you always get the same answer. It has nothing to do with Lorentz invariance. It just has to do with doing calculus properly. Yes.
Again, the step from the next to last one to the last one.
Yeah, the derivative of a theta function, from the next to the last to the last. Well, that's the same step here. The derivative of this thing is n mu dot delta of x by the chain rule for differentiation.
I guess we have n prime dot x to prime dot.
Oh, I just dropped the prime. You want me to keep it? Then I'll drop it in the next equation. Okay, it's an integration variable. It doesn't matter. Now, this concludes our discussion of continuous symmetries. All I will have to say about them in general. But of course, there are all sorts of symmetries in nature that are not continuous, that are not part of some connected group that contains the identity transformation. Among them are such old friends from non-relativistic quantum mechanics as parity and time reversal. So we will now study discrete symmetries. That is to say, transformations where phi of x goes into some transformed field, phi prime of x, but there's no parameter in the problem. Just does it. There's no such thing as a parity transformation by 7 degrees. There's just parity, space reflection, or no space reflection. It's not like a rotation. We'll assume these things are symmetries in the usual sense. That is to say, the action, integral d for x of L of phi and d mu phi equals the action. There, of course, may be many of them. Integral d for x L of phi prime. I leave off the indices out of sheer laziness. D mu phi prime. For at least for appropriately chosen boundaries. Yes, sir. Well, there are cases where the Lagrangian is obviously not invariant, like parity. The Lagrange density Lagrange density is obviously not invariant. The Lagrange density at point x is turned into Lagrange density at point minus x. There, the Lagrangian, which is the space integral of the Lagrange density, is invariant, though. On the other hand, for the case of time reversal, the Lagrangian at time t is turned into Lagrangian at time minus t. And it's only if you integrate among time symmetric in t1 and t2, t1 equals minus t2, that you get the action invariant. So this is more general, and I'll assume that.
Do you have to adopt that also for continuous?
Well, we adopted a more special definition that in particular implies this, that the action only picks up boundary terms. Okay. This part of the discussion is going to be rough and heuristic. We'll give particular instances rather than developing a general theory. So don't worry about too precisely about what I mean by an invariance. Now, in a rough and heuristic way, as I said, we would expect such a transformation, of course, is a symmetry of classical physics. And in terms of classical physics, it does what a symmetry always does. It enables you to generate new solutions of the equation of motion out of old solutions. But in general, it is not connected with the conservation law, as continuous symmetries are. However, we would expect in quantum physics, although there should be no Hermitian operator associated with these things, no Hermitian operator that generates the infinitesimal transformation, for the excellent reason that there is no infinitesimal transformation, we would expect there to be a unitary operator that affects the finite transformation. Indeed, the argument, I give a rough and ready argument, everything is determined from the action by appropriate variations and canonical quantizations and whatnot. If the action is the same for phi as it is for phi prime, then we should, for everything we do, there should be a one-to-one Hilbert correspondence between the Hilbert space we get by doing things in terms of phi and the Hilbert space we get by doing things in terms of phi prime, since every step is step by step the same, and therefore is a unitary transformation that turns phi into phi prime. So, rough, very rough, okay? But just qualitatively, if it doesn't change the action, it can't change the quantum mechanics, and that means there's a unitary transformation. You know it's rough because you know it's a lie for time reversal, where there's not a unitary transformation, but we won't get to that until next lecture. Now, this is just rough for orientation. Let's do some particular cases where we can simply see what is going on and see whether or not there is a unitary transformation or not. The first case I will turn to is our good old example of two free fields of the same mass. Minus, thank you. Good that you remember it. This is a, on a formal level, everything I say will also be true, of course, if there's an interaction, say, of this form, for a typical example. Now, there is, I said that this system was SO2 invariant, but in fact it's larger than, it has a larger invariance group of internal symmetries. I should have written an example, a discrete internal symmetry. has full O2 invariance. That is to say, it is invariant not just under proper rotations, but under improper rotations. Not just under rotations, but also under reflections. Now, of course, we've already studied all the consequences of the rotations, and since every reflection is the product of some standard reflection and a rotation, we might as well just consider one standard reflection, which I will choose, since I am the one who sets the standards here, to be the transformation phi 1 goes into phi 1, phi 2 goes into minus phi 2. We can easily see that there is a unitary at least in the case of the free field, where we can explore the Hilbert space completely. In the general case, if we are willing to extract from non-relativistic quantum mechanics the statement that any operation that doesn't change the canonical commutators is unitarily implementable, we can easily see that there is a unitary transformation that does this. In the free case, g equals 0, we just read off from this that if there is a unitary transformation such that this is u phi 1 u adjoint, and this is u phi 2 u adjoint, that unitary transformation has the property that it turns ak1 into ak1 and ak2 into minus ak2, and the same things for the creation operators, of course, just by taking the adjoint. Really, my convention is always the adjoint on the left, isn't it? I'll adopt that. It doesn't matter in this case, but I don't want to confuse you more than I have to. Now, it's obvious to see that there is a unitary transformation that does this. It is simply a transformation that, acting on states with a definite number of particles of type 1 and a definite number of particles of type 2, multiplies the state by minus 1 to the number of 2 type particles. That obviously has the desired property. Thus, there is, as expected, in the free case where we can do things explicitly, there is a unitary transformation that does this. This unitary transformation is perhaps more simply expressed in terms of the B's and the C's. You recall BK was AK1 plus IAK2 over root 2, and CK was AK1 minus IAK2 over root 2. Thus, this unitary transformation has the property that UBK U adjoint equals CK, and UCK U adjoint equals minus CK. Yes, again, it doesn't matter in this case, as I will shortly demonstrate, but thank you. No minus, I'm sorry. It's just a plain old BK. You change the sign of phi, you change the sign of the two thing, and you interchange these two things. Thus, equally well, you could say this is a unitary transformation which, acting on any state, turns all the B-type particles into C-type particles and all the C-type particles into B-type particles. Such a transformation is called a charge conjugation. Conjugation is a bad word. It sounds like it shouldn't be unitary. Complex conjugation is not a unitary operation, but it is called charge conjugation. It should better be called perhaps particle-antiparticle exchange, because this is the structure of the transformation that exchanges particles and antiparticles, exchanges pi pluses and pi minuses, for example. And for this reason, we normally call it C and put a little subscript C on all of these objects to tell you that that's the transformation it's associated with. In general, as I said before, when we have a unitary operator is not an observable, and therefore we normally don't get a conserved quantity, even though the unitary operator may commute with the Hamiltonian. However, there is one special case in which a unitary operator does give us a conserved operator, when the unitary operator is itself Hermitian. This happens in this case because UC squared equals 1. You turn every B-type particle into a C-type particle, and then you turn it back again into a B-type particle. This is, of course, also UC adjoint. And dividing by UC on the left, we see that UC equals UC adjoint. That is to say, UC is both unitary and Hermitian. That is rather obvious in terms of its representation in terms of 1 and 2 type particles, where I told you that its eigenvalues were +1 and -1, numbers that are both of modulus 1 and real. So in this particular case, even though this is not associated with a continuous symmetry, we can take states and divide them up, if we wish, into eigenstates of unitary charge conjugation operator, because it is also a Hermitian operator. This is usually not done in practice except when you have equal numbers of particles and antiparticles, the terminology we now use for kinds of particles connected by this kind of transformation. If you have equal numbers of particles and antiparticles, if you're considering states of a pi plus, pi minus system, for example, you may well wish to divide them up into states that are charge conjugation even and charge conjugation odd, depending upon whether the wave function is symmetric or antisymmetric under exchange of the pi plus and pi minus variables, and use the fact that charge conjugation commutes with the Hamiltonian to deduce consequences for transition amplitudes. Actually, we won't do that for pi pluses and pi minuses because you gain no information there that you don't gain from parity. But we will use it for electrons and positrons where you do gain additional information. Well, I have mentioned the magic word pair. Are there any questions on this thing? I mean, I haven't deduced particle-antiparticle symmetry. Don't think anything like that. Okay, I've simply given an example of a theory which I have cooked up to possess a symmetry that is structurally similar to a symmetry I know exists in nature by experiment, just to show you how such a symmetry could arise within the context of Lagrangian field theory. Are there any questions about this symmetry and the unitary operator that implements it? Questions? I noticed blank expressions. The people who have I've gone too fast through some of the earlier statements. Ask me now. It's never too late for a question. Yes? So charge conjugation is also. Oh, CPT is very different. That's something we won't get to until the very late in this course if we bother to do it at all. But in fact, you can show just from general assumptions of field theory, from Lorentz invariance, positivity of the energy, and locality, the fact that fields commute at space-like separations, without making any assumption about a particular Lagrangian, about the form of the Lagrangian at all, or even whether things are derived from the Lagrangian, you can show that there is CPT invariance. This is the famous Cpt theorem. We believe this is the reason why, although one after another, parity, time reversal, and charge conjugation have fallen to experimenters, CPT remains unchanged. Indeed, the most revolutionary conceivable experimental result at the moment, well, violation of conservation of energy would also be pretty revolutionary. But one of the most revolutionary ones would be that the CPT would be found to be violated. If that were so, we would not only have to sacrifice all of the particular theories which we now have, which we hope explain the world, we would not only have to sacrifice the general ideas of, we would have to sacrifice the general idea of a Lagrangian field theory, and indeed the general idea of local fields. It would be back to lecture 1. This whole course would be canceled out. Now, I would like to discuss parity, and I would like to run around 5 minutes overtime also, because it's a 10-minute discussion. as my next example. I will tell you what I mean by a parity invariance. In this case, I will show that parity can be very strange, and I hope amuse you by cooking up a bunch of theories, most of which have no particular resemblance to nature, in which parity has strange properties. A parity transformation, I will say, is any transformation of the form sum unrepeated indices as always implied. It turns the fields at a point x into some linear combination of the fields at the point minus x, and is of course supposed to be an invariance. There is, I put no restrictions on the matrix MAB. Some will come out in particular examples. And I don't know, say, whether my fields are scalar or pseudo-scalar or something even stranger. They may dance among themselves in a complicated way. As long as it turns all of the observables at point x into all of the observables at point minus x and is a symmetry, it is parity by me. First example. Of course, I'll explicitly display the unitary transformation only for free field theory, but I'll discuss the invariance on a classical level for a wider variety of theories. First example, L equals 1/2 d mu phi squared minus mu squared over 2 phi squared. I just got tired of writing d upper mu, d lower mu. You know what that means. Plus g minus g phi fourth. This obviously possesses a parity invariance. Phi of x and t goes into phi of minus x and t. This is an invariance of parity type. It doesn't change. It, of course, changes the Lagrange density at point x into the Lagrange density at point minus x, but it doesn't change the action. In the case g equals 0, it is obviously implemented by a unitary transformation which turns either a creation and annihilation operator at point k into a creation and annihilation operator at point minus k. The proof is simple. Apply this to the definition of the free fields and then change the integration variable k to the integration variable minus k, which turns x into minus x and doesn't change t. Thus, parity takes a particle going this way and turns it into a particle going this way. The usual thing that parity does in non-relativistic particle physics. A completely alternative transformation, which I will call p prime, which is also an invariance of the Lagrangian, is phi of x and t goes into minus phi of minus x and t. This is also an invariance if this is, because in particular this Lagrangian is invariant under phi goes into minus phi, a trivial internal symmetry, closely corresponding to what we did to phi 2 in the discussion of charge conjugation, and the product of two symmetries is a symmetry. This transformation law is called the Scalar Transformation Law, and this is called the Pseudo Scalar. It is merely a matter of convention for this particular theory whether you say phi is a scalar field or phi is a pseudo-scalar field. First important point. This theory has two symmetries, among others, one which is C-like and one which is P-like, and therefore the product, Cp, is a symmetry, and which you call parity and which you call charge conjugation, or phi into minus phi times parity, is a matter of your taste. Nobody can fault you. What is important is the total group of symmetries admitted by the Lagrangian, from which one draws all sorts of physical consequences, not what names one attaches to individual members. Okay, is this point clear? Because it is a source of much confusion. As long as you have one possible definition of parity, as long as you have internal symmetries around, you can always adopt a new nomenclatural convention in which you take the product of one of those internal symmetries and parity and call it parity. And call your original parity the product of your new parity and the inverse internal symmetry. Nobody can stop you, and nobody should. As long as when you are writing your papers or giving your lectures, you are clear about what convention you are using, it is harmless. Of course, if the Lagrangian does not have the internal symmetry, then you might end up with a unique definition of parity, because there will be no internal symmetries from which you can multiply parity. For example, if I take the same Lagrangian as before and add to it a term h phi cubed, then phi into minus phi is no longer a good definition of parity and is no longer a symmetry, and the only sensible definition of parity is scalar without the minus sign. Pseudo scalar, no. Because you can call that parity if you want, but then you have got yourself into the position of saying this theory is not parity conserving, which is obviously a silly thing to say. Yes, sir?
What if you have three fields, right? And that's is still continuing whether you call them scalar or pseudo scalar?
Absolutely. Well, it depends. Yeah, an isospin triplet, in fact, phi into minus phi is always a symmetry, at least if they're not interacting with Fermi fields or other things. That's a separate...
But then when you do that, it does matter.
It doesn't. It depends on the form of the interaction. Sometimes it does and sometimes it doesn't. Okay? In nature, there's no point in... If you want to ask about the real world, if you consider the weak interactions, there is no sensible definition of parity, because there's no way of defining it so the weak interactions preserve parity. If you throw away the weak interactions, you have a lot of internal symmetries. For example, you have the conservation of electric charge. Well, in fact, you have five. You have the continuous groups, one-parameter groups corresponding to electron number, muon number, nucleon number, electric charge, and strangeness. Those all commute with each other. They're commuting U1 groups, okay? And for that reason, it is a matter of convention what the relative parity of the electron and the muon is, because you can always use muon number to multiply into your definition of parity and change the parity of the muon and the muon neutrino and nothing else. It is a matter of convention what the relative parity of the electron and the proton are. It is a matter of convention what the relative parity of the proton and the lambda hyperon are. That you use strangeness for. Okay? And as a matter of convention, what the relative parity of, let's see. No, I guess I've used everything. Well, doesn't matter. Those are four things that are totally matters of convention. These conventions are normally established so that all those relative parities are +1, but that's just a convention. Okay? If physics had developed into in a different way historically, and the early papers had been written differently, someone might have said the relative parity of the electron and the proton is -1, and then we would all be saying that. That would be our convention. Okay? Other questions? Now I will continue the argument. I have shown you an example where scalar fields, the scalar transformation law is an okay definition of parity, but the pseudo-scalar is not. I will now construct an example where it goes the other way. These examples are rather unnatural involving scalar fields, but we will find when we talk about fermions, we will find we can write very simple interactions that have this property. But for show it to, I can be shown with scalar fields, but I have to write down a grotesque sort of interaction. I will have to introduce the epsilon symbol, or epsilon tensor, as it is sometimes called. You are probably all familiar with the three-dimensional epsilon symbol, epsilon ijk, which is defined to be completely antisymmetric, which means, in particular, that you know all of its values if you know epsilon 1, 2, 3, and epsilon 1, 2, 3 equals 1. From this, you can construct a object that is a scalar under rotations, ai, bj, ck, which is sometimes known as the triple scalar product, A dot B cross C, as you can easily see by writing it out, and which has funny transformation properties under parity if A, B, and C have simple transformation properties under parity. One can perform precisely the same trick in 4 dimensions. One defines an object epsilon mu nu lambda sigma that is also completely antisymmetric, and epsilon 0, 1, 2, 3 equals 1. From this and for 4-dimensional vectors, one can form a Lorentz scalar, but it will have funny parity properties. I will now give an example of how to make something where pseudoscalarity is forced. L equals a free Lagrangian for 4 scalar fields. I won't bother to write down the 4 terms, but there are just 4 of them, and they have 4 different masses. Then G, phi 1/4 plus phi 2/4 plus phi 3/4 plus phi 4/4 plus F epsilon mu nu lambda sigma d mu phi 1 d nu phi 2 d lambda phi 3 d sigma phi 4. If you want to leave early, but there's a problem set waiting for you up here. Please don't forget it. This object, if we were to declare all 4 fields, then we would also have to declare that this term breaks parity. Because as you notice, every term involves 1 time index and 3 space indices. The space derivatives change sign under parity, and the time derivatives do not. So therefore, we pile up 3 minus signs when we parity transform this object, which is a disaster since 3 minus signs changes the sign. We have to declare that one of the fields is pseudoscalar and 3 of the fields are scalar. Since we have, of course, total freedom to make a whole large group of internal transformations where we change the signs of phi 1, phi 2, phi 3, and phi 4 as we wish, it is a matter of taste which of the 4 we call pseudoscalar. That is just a matter of how we multiply an internal symmetry by a parity. On the other hand, if I were to add to this h phi 1q plus etc., then there would be no good definition of parity, because I have to have a minus sign in one of the fields to make this thing work out all right. But then this thing gives me disaster. And whether I choose scalar or pseudoscalar and in what combination, it doesn't matter. There is no good definition of parity. There is no symmetry that can be interpreted as a parity.
Do you mean if you add H in addition to the F, or do you mean
No, in addition to. H by itself would allow everything to be scalar. Now this demonstration might let you to think the only ambiguity is a plus sign or a minus sign, whether the particles have intrinsic positive parity or intrinsic negative parity. I will now give a demonstration where the only possible definition of parity has an I in it. This will be super grotesque and will involve a complex field. So my free Lagrangian is now to be considered as having 5 fields in it. 4 fields with some 4 masses and a complex field with some 5th mass. You still have this H term that keeps me from changing the term of the coefficient of the sign of the scalar fields. And I now multiply this last term, just the last term, it looks pretty silly, huh? But it's Hermitian. It's got all the properties you want. It's a 6 linear form in the fields with an epsilon tensor, a very grotesque object, not one we will encounter in any of the theories we will take seriously, but it's still an amusing example. I observe that this theory has a pure parity in which phi a of x and t all go into phi x and t, a equals 1, 2, 3, 4. And psi of x and t goes into I, psi of x and t minus x and t, supplying the missing minus sign from I squared. This is just for fun, but it is an example where the square of parity is so strange. This is the only possible, this and the minor variations with a minus I in place of an I. You can readily convince yourself for this grotesque theory, the only possible parities that will work. And in this case, things are so strange that the square of parity is not even 1. The square of parity is 1 on the 4 real fields and minus 1 on the complex field. Therefore, if you ever read a paper in which someone says, on general a priori grounds, the square, we put the condition that the square of parity must be 1, tell him about this, send him a postcard telling him about this example. He may say, oh, I wouldn't call that parity. But then you would say he was being pretty foolish, because if the world really were like this, there would be this very useful symmetry that turns observables at the point x into observables at the point minus x, and which puts all sorts of restrictions on scattering cross-sections and energy levels and all the things a symmetry usually does. And a square happens to be not 1. If he doesn't want to call that parity, what is he going to call it? Okay, that's the end of the philosophical part of the discussion and also of this lecture. Next lecture, time reversal and the beginning of perturbation theory.